Welcome back to the channel. Today we're diving into a new topic called dynamic programming, or DP for short. We'll start by breaking down what DP is and how it works, then put our knowledge into practice by solving the classic Fibonacci number problem. This will serve as a great foundation for our upcoming videos, where we'll tackle more challenging medium and higher level problems using DP. So let's get started. So first of all, what's dynamic programming, or DP? For short, it is an approach to solve problems by breaking them into smaller subproblems, solving each only once. So this statement here, solving each only once, is very important because it drives the overall solution, the overall solution time complexity, and also by applying this approach, we will be reusing the result of these smaller subproblems. So that's the key idea of dynamic programming, to see how we can break a problem into smaller subproblems and then to solve each subproblem individually and then combine those results somehow to build up the final solution. When to use dynamic programming? Well, when the problem has overlapping subproblems, that's like a general rule of thumb. So that kind of problems are will most likely be applicable to dynamic programming, to DP. There are two common approaches. One is top-down, or memoization. It's a combination of recursion plus caching the results. So basically, it is a way to solve the problem using the recursion, but to optimize the recursion with some additional structures where we will store the results of the subproblem, so we don't need to recalculate them every time. And another common approach would be bottom-up, or tabulation, which is quite opposite. So in top-down approach, we are starting with the overall problem and we are solving it recursively by breaking it down into smaller subproblems. But here, bottom-up approach is opposite in the way that we start with solving the smaller problems and then we are iteratively building up the solution of we are iteratively heading towards the final solution by combining the results of the smaller problems. So I hope this makes sense, and I'm sure it's gonna be more clear when we switch to the actual problem. So for today we are starting with the classic Fibonacci problem, which is on LeetCode, which is the LeetCode problem number 509. It is an easy problem, definitely, but it's a great problem to learn dynamic programming, and we will start with a naive approach, which is not a DP approach, and then we will see how we can apply both approaches, top-down and bottom-up, to solve the same Fibonacci problem and to find a more efficient solution. So first, let's go through the problem description. So the Fibonacci numbers, commonly denoted as f of n, form a sequence called the Fibonacci sequence, such that each number is the sum of the two preceding ones, starting from 0 and 1. That is, f of 0 is equal to 0, f of 1 is equal to 1, and then every next element is calculated using this formula. F of n is equal to f of n minus 1 plus f of n minus 2. Basically, the element in the Fibonacci sequence is calculated as the sum of the previous two elements, with exemption of the first two elements that are basically hard-coded to 0 and 1. So the first element is 0, the second element is 1, and every next element is calculated as the sum of the previous two elements. So let's write down a couple of a few numbers in the sequence. So let's say that n, in the first row I'll write n values, and in the second I will write the f of n, or Fibonacci of n. So when the first element is 0, or which has the index 0, or let's call it when n is 0, f of n is 0. Then the next element is 1. When n is 1, the f of 1 is 1. And then every next element is calculated as the sum of the previous two. So the next will be 1, and then 2, and then 3, and then 5, and then 8, and then 13, then 21, and so on. So when n is 2, it's 1, the f of 2 is 1, the f of 3 is 2, the f of 4 is 3, the f of 5 is 5, the f of 6 is 8, the f of 7 is 13, and the f of 8 is 21, and so on. F of 9 would be 34, if I'm not mistaken, and so on. So it's quite straightforward formula to explain the Fibonacci sequence. And now let's see how we can solve this problem. So our goal is to, given the number n as an input, to calculate the f of n following this formula. So here are two examples. When n is 2, the output should be 1. When n is 3, the output should be 2. Basically, when n is 2, output is 1. Why 1? Because it's calculated as a sum of the previous two numbers, 0 and 1, and so on. So we basically need to implement the method which will have an integer as a return type, which can be called fib, and which takes an input, an integer n called n as an input parameter, and yeah, the output should be the f of n, or fib of n value in this sequence. So what would be a naive approach here would be to simply follow this formula, and we can calculate the desired element. So first of all, n, we can assume that it's going to be an integer greater than or equal to 0. So no negative numbers will be provided. However, if you want, maybe a good approach would be to simply check that at the beginning. So if n is less than 0, we can simply throw an illegal argument exception. Invalid input n. By the way, as always, I will be using Java programming language, but yeah, it should be straightforward to implement this in any other language. So how can we solve this problem? Yeah, well, as I said earlier, we can follow this pattern. So we can say if n is 0 or if n is 1, the solution should be 0 or 1, right? So we can say something like this. We can say simply return n. Why n? Because when n is 0, the solution should be 0 as well. When n is 1, the solution should be 1 as well. Another alternative approach would be to say if n is 0, return 0, and then another if statement, if n is 1, return 1. But why having two if blocks when we can do it in a single block? Okay, and then if we are here, that means that n is not less than 0, that n is not 0, and then that n is not 1. So it's a number greater than 1, so it's 2, 3, 4, and so on. So in this case, we can simply return, we can follow this formula and we can return, we can call this method recursively, and we can return fib of n minus 1 plus fib of n minus 2. Okay, as simple as that. And this should be the solution of this problem. A naive solution, I'd say, because we will see later that it's not that optimal, it's not that efficient. So here, so I added this method into a class called solution. So here in the main method, let's just try this out. So solution equal to new solution, and we can say something like this. It's not println. Result is solution.fib of, let's say which number we want to take. Let's say fib of 7 should be 13, right? Yeah, and the solution is 13. That's correct. Let's say another fib of maybe 5 should be 5. Yeah, result is 5, and if you see here, that's the expected result. So this is fine, this works well. However, let's try to dive deep into the time complexity of this solution. So let's see what would be the issue with this approach. So let's say we need to calculate fib or f of 5. So by following this recursive formula, recurrent formula, it should be f of 4, right, plus f of 3. And then this f of 4 will be broken down to f of 3 plus f of 2, right? And this f of 3 will be calculated as f of 2 plus f of 1, okay? Let's move forward. So f of 3 is f of 2 plus f of 1, plus this f of 2 is f of 1 plus f of 0. This f of 2 is again f of 1 plus f of 0. And this f of 1 is just 1, okay? And this is then equal, this f of 2 is f of 1 plus f of 0 plus f of 1 plus f of 1 is 1 plus f of 1 is 1 plus f of 0 is 0 plus f of 1 is 1 and plus f of 0 is 0 plus 1. And finally, this is equal to f of 1 is 1 plus 0 plus, here we have 3, 4 plus 4, right? Which is equal to 5. Okay, and this is the solution. This is how this approach works under the hood. And do we see an issue with this approach? Well, we can see that certain values have been calculated or a couple of times. Let's see here. So here, to calculate f of 4 plus f of 3, we need to calculate f of 3, which will be calculated as f of 2 plus f of 1, and so on. Similarly, for other values, we end up solving a similar problem multiple times. You see how many times f of 2 or f of 1 is called. It's called 1, 2, 3, 4, 5 times, okay? we have f of 1 called 5 times, and every time we need to call this method recursively and to solve the same problem instead. So we are wasting our time to solving a similar sub-problem multiple times, and that's why this approach is not that efficient. So if you would check the time complexity, it turns out that it has an exponential time complexity, which is quite bad for a time complexity. And why it's bad? Because the exponential function grows really fast. So for relatively small numbers, it would take a lot of time to calculate the solution. So let's say when n is, I don't know, 32 or 64, for instance, the solution would spend a lot of time. Let's see, let's try to run solution for when n is 64, and let's see what happens. You see, it takes a lot of time to calculate the solution. So it struggles to solve this problem because the overall solution of our problem has exponential complexity. So it basically will spend 2 over 64 instructions to calculate this the solution. So I'll stop this execution, and let's see how we can use dynamic programming to basically to optimize this solution. So instead of us recalculating the same problem multiple times, we can apply the dynamic programming top-down approach or memoization. So we will use a map structure, and we will store the solution of the sub-problems in that map. And anytime we need to calculate, let's say, fib of 2, if this has been calculated already, we will just check in that map and see if we have the solution for this fib of 2. Let's just take the solution and not recalculating it again. Okay, so how we can apply the dynamic programming solution here. So let's call this, let's basically fix this fib method directly. So to solve this problem, we will create a map called, which will be integer map, and we can call it cache. It's like a cache memory. Okay, and this map will be used to store the solution of the sub problems. So if n is less than 0, we can throw an illegal argument exception. If it's 0 or 1, we can simply immediately return the solution. No need to do anything else. But if it's greater than n, before applying this recursive call, let's see in the cache whether we already have the solution for n. So we can say something like this: if cache contains key n, we can simply return that value. But if it doesn't contain the value n, if it doesn't contain it, that means that this is the first time we are solving this sub problem for the provided n, and we need to calculate it, put it into the cache, and return the result. So here, instead of immediately returning the solution, we can say int result is equal to this, and then we can put it inside the cache, cache.put for the key n value result, and then we can return the result. Okay? And this should work. If you are unfamiliar with how maps work, it's a structure which works as a key value store, where the first parameter of the map is the type of the key. The second parameter here is the type of the value, and it's designed in a way that it can efficiently store a value inside the cache, and if for a given key, it can efficiently, in constant time, retrieve that value from the cache. So it's super efficient. And if let's first try to see whether this approach works at all. So let's call it for the value 7, and the solution is 13, as expected. For n7, the solution should be 13, right? But let's now try running this example for 64, when n is 64, and it immediately tells us the result. So you can see how a small difference can make such a huge change in the time, speaking of the time complexity with regards to the time complexity of the solution. Okay, so we managed to solve the Fibonacci problem using the dynamic programming approach, and we managed to find the optimal solution when it comes to the time complexity. Okay, so basically, what would be the time complexity of this solution? The time complexity would be big O of n. So it's a linear time complexity. Why big O of n? Because when n is 1 or when n is 0, it immediately returns the solution. When n is present in the cache, it immediately returns the solution. So this is O big O of 1 time complexity. And basically, it calls fib of n-1 plus fib of n-2, meaning that for every value 0, 1, 2, 3, 4, 5, 6, and so on until all the way to n, it will calculate the solution only once, right? And because of that, the overall time complexity will be linear. So we never have to iterate through anything. We just need to calculate all the values basically from the beginning to the end. So it will calculate the values in one direction. Okay? So the time complexity of the solution is linear. And let's quickly see what else we can do. So basically, we have solved this problem using dynamic programming top-down approach. Let's see how we can solve it using the bottom-up approach. In my opinion, it's even more intuitive. And let's see what can also be improved here. We improved significantly the time complexity. We managed to find the optimal solution, but we can also improve the space complexity of the solution. Here we are using an additional data structure, which is cache, or which is a map actually. But here we can probably solve this problem without need for an additional linear space complexity data structure. So how can we do it? Let's call it, let's add the method public int fib, let's call it fib2 int n. So how can we do it? So to apply the bottom-up approach, we can start, if we need to calculate the fib of 7, we can calculate fib of 0 and fib of 1, and then we can calculate the fib of 2 as fib of 0 plus fib of 1, and we can memorize all the solutions in an array. The length of the array will be equal to n. But even that can be improved. Every time we need to calculate fib of 5, for instance, we don't need to keep track of all the previous solutions of the subproblem. We just need to keep track of the previous 2 solutions. So basically, instead of storing all the solution in a cache or in an array, we can simply take 2 variables and keep track of the previous 2 solutions, and anytime we need to calculate the next solution, we can just simply take the previous two values. Okay? It's as simple as that. So to solve this, we can say something like this. So we can have the same check at the beginning. If n is less than 0, we can throw an exception. If n is 0 or 1, we can return n. But if it's greater than 1, we can solve this problem by introducing 2 variables. One can be called prev, like previous, which is initially 0, and we can have a variable called current, which is 1. And we can say for int I equal 2, so we are starting from the 3rd element, while I is less than or equal than n, because we need to find a fib of n, I plus plus. So current will be equal to current value, or next, we can call it next. Int next is equal to current plus previous, or we can call this prev1, prev2, and prev1, because those are both previous values. So it can be prev1 plus prev2, and we can say prev1 will become next, and prev2 will become what prev1 used to be. Prev2 will become prev1. So something like this. And at the end, we can just return prev1. So 3rd element is equal to the previous 2 elements, sum of the previous 2 elements, and then prev2 will be equal to prev1, and prev1 will be next. Let's try to call fib2 of 7. And the result is 13, as expected. Let's call fib2 of 1. It should be 1, right? The result is 1. Let's call fib2 of 64, the big solution, and it calculates it immediately. Let's see, result fib2 of maybe, I don't know, 5. It should be 5. Okay, so this works too. So this is a bottom up approach. We start with smaller problems first, and then we build up the final solution. So to calculate fib of n, we need to calculate all the values, fib of 0, fib of 1, fib of 2, fib of 3, fib of 4, all the way to fib of n. How we do it? How we can do it? We can use two additional variables called prev1 and prev2, which will keep track of the last two elements in the Fibonacci sequence, and we can eliminate this next element, but yeah, even this solution is quite efficient as well. So the next element is equal to the previous two elements, so there is no need to store all the solutions before. We can simply just keep track of the last two solutions of the subproblems, and the solution at the end will be in this prev1 variable. So basically you can look into this fib2 solution as when someone asks you to calculate f of n, you will simply go and calculate the first, second, third, fourth, fifth element, and so on, all the way to n. And every time we are calculating an element, you are just taking previous two solutions into account, and you just need the last two elements or the previous two elements to keep track of. So it's quite efficient. So it has the time complexity of big O of n, but also it has the space complexity. So time complexity is big O of n, but in this case space complexity is big O of 1. So it has a constant space complexity because it doesn't need to store all the solutions, but only the previous two solutions, which is basically additional two variables. So I hope that you like this video. As I said at the beginning, in the next few videos we'll be solving more challenging dynamic programming based problems. So we'll probably start with a couple of medium difficulty problems on LeetCode, and after that we will switch to some hard difficulty problems. And yeah, I'll see you in the next video. Thank you.